Uranus is lying on its side. Not tilted slightly, the way Earth is tilted at 23 degrees and produces seasons, not leaning gently, the way most planets lean. Uranus is tilted at 98 degrees. Its axis of rotation points almost directly at the Sun. It does not spin upright like a top. It rolls through space like a ball, its poles taking turns pointing toward the Sun for decades at a time, its equator running nearly vertical to the plane of its orbit. This is not normal. This is not a feature of how planets form. This is the signature of a catastrophe, the frozen record of a collision so violent that it permanently altered the orientation of a planet 4 times the size of Earth. Something hit Uranus. Something massive, something fast, something that arrived with enough energy to knock a world the size of a small giant onto its side and leave it there for the 4.5 billion years since. And we do not know what it was. We do not know where it came from. We do not know whether it still exists somewhere in the solar system or was destroyed in the impact. We do not know exactly how large it was, or what it was made of, or how many times it hit, or whether the hit was a single catastrophic event or something more complex. What we know is what Uranus looks like now, and what it looks like now is a planet that was hit so hard it never recovered. First, let's understand what normal looks like, because Uranus is the opposite of it. The 8 planets of our solar system all formed from the same rotating disk of gas and dust that surrounded the young Sun approximately 4.5 billion years ago. That disk rotated in a specific direction. The planets that formed from it inherited that rotation. They orbit the Sun in the same direction, in nearly the same plane, and they spin in roughly the same direction as their orbit. Most of them are upright or close to it. Earth is tilted 23 degrees, a moderate lean that produces our seasons. Mars is tilted 25 degrees. Saturn is tilted 27. Jupiter, the largest planet in the solar system, is tilted only 3 degrees, nearly perfectly upright. Venus is an oddity. It is tilted 177 degrees, meaning it spins in the opposite direction to most planets, effectively upside down. But Venus's slow rotation and dense atmosphere complicate the picture. Uranus is different from all of them. 98 degrees, past perpendicular, rolled so far onto its side that its north pole points below the plane of the solar system for half of each orbit, and above it for the other half. During Uranian summer at one pole, the Sun shines directly overhead for decades. The opposite pole spends the same decades in total darkness. Then they switch. A Uranian year lasts 84 Earth years. The polar regions spend 42 years in continuous sunlight and 42 years in continuous darkness. The equatorial regions, meanwhile, experience a version of day and night, but the Sun barely rises above the horizon, skimming around it in a shallow path that changes slowly as the decades pass. No other planet in the solar system has seasons like this. No other planet has weather like this. No other planet has a history like this. Something made it this way. The leading explanation, and it has been the leading explanation for decades, is a giant impact. In the early solar system, the giant planets were not yet in their current orbits. Jupiter, Saturn, Uranus, and Neptune were still migrating, moving outward under the influence of gravitational interactions with the disk of debris and the gravitational resonances between themselves. The outer solar system was crowded and chaotic. Large objects, planetesimals, proto-planets, bodies ranging from the size of asteroids to the size of small planets, were abundant and moving on crossing trajectories. In this environment, collisions between large bodies were not unusual. The Moon formed from such a collision. Mars has hemispheric asymmetry that may be the scar of a giant impact. The unusual density of Mercury may be explained by a collision that stripped away much of its original mantle. Giant impacts were a feature of the early solar system, not an exception. What hit Uranus was not a small body. To tip a planet with 14 times Earth's mass by 98 degrees from near upright to nearly sideways requires an impactor of substantial size. Current estimates, based on simulations of the impact geometry and energy transfer, suggest an impactor somewhere between 1 and 3 Earth masses. A rocky or icy protoplanet, roughly the size of Earth or somewhat larger, striking Uranus at a significant angle. The collision would not have been instantaneous. A body 1 to 3 Earth masses colliding with Uranus would have produced an impact event lasting minutes to hours, a planetary-scale cataclysm in which the impactor's material was partially absorbed into Uranus's interior, partially ejected into orbit around Uranus, and partially scattered across the outer solar system. The axis tipped permanently. Physics does not offer a mechanism to tip it back. But here is where the story becomes more complicated than a single impact. If a single large impactor hit Uranus and tipped its axis, the simulations of that event produce a specific set of predictions about what Uranus should look like today. The simulations do not fully match the observations. Uranus has a magnetic field. It is a strange magnetic field, not aligned with the rotation axis as Earth's magnetic field roughly is, but tilted at approximately 60 degrees to the rotation axis and offset from the planet's center. It's a lopsided, asymmetric field that produces a magnetosphere unlike any other in the solar system. Neptune also has an asymmetric, offset magnetic field, similar in character to Uranus's, which is interesting because Neptune has a much more normal axial tilt of 28 degrees. The similarity of the magnetic fields of two planets with very different tilts suggests that the magnetic field geometry may not be entirely a consequence of the impact. Uranus is also anomalously cold. Uranus radiates almost no internal heat. Jupiter, Saturn, and Neptune all radiate significantly more energy than they receive from the Sun. Their interiors are still cooling from their formation, still releasing heat that produces weather patterns and drives atmospheric dynamics. Uranus is different. Its heat output is near zero. It is not releasing significant internal heat. This is strange for a planet its size. It should still be warm inside. Its formation 4.5 billion years ago should have left a thermal legacy that persists. But Uranus is cold, colder than Neptune, despite being closer to the Sun.
The giant impact hypothesis offers an explanation. If the impactor created a layer of high mean molecular weight material, heavy elements from the impactor mixed into the interior, that layer could act as a thermal blanket, trapping the internal heat and preventing it from escaping to the surface. But the simulations that produce the right axial tilt do not always produce the right internal structure. And the simulations that produce the right internal structure do not always reproduce the axial tilt correctly. Something is missing from the models. In 2018, a team at Durham University ran the most detailed simulations of the Uranus impact event yet attempted. They used smoothed particle hydrodynamics, a computational method that models fluids and gases as collections of interacting particles, to simulate the collision at resolutions that previous models could not achieve. Their results were illuminating and inconclusive in equal measure. A single grazing impact, an impactor striking Uranus at an oblique angle, roughly 45 degrees, could produce the observed axial tilt without mixing the impactor's material deeply into Uranus's core. This would explain the thermal suppression. The heavy material would be deposited in a shell around the core, creating the insulating layer. It would also explain why Uranus's interior appears relatively undisturbed despite the extreme tilt. A head-on collision, a direct impact at a steeper angle, would mix the impactor material more deeply, produce a larger thermal perturbation, and potentially explain different aspects of the observed structure. Neither geometry explained everything. The magnetic field remained a problem. The simulations could not reproduce the specific off-center tilted geometry of Uranus's magnetic field from a single impact event in any of the configurations they tested. The Durham team noted that multiple impacts, 2 or more smaller objects rather than one large one, could potentially explain the combination of observations better than any single impact scenario. 2 impacts, 2 unknown objects from an early solar system that no longer exists in the form it had when they struck. There is a detail about Uranus that gets less attention than the axial tilt, but may be equally important. Uranus has 27 known moons. All of them orbit in the plane of Uranus's equator, which means all of them orbit at the same 98-degree tilt as the planet itself. They did not form in the plane of the solar system and get tilted later. They orbit as if Uranus's sideways tilt is simply the normal configuration. This is consistent with the moons forming after the impact, accreting from the debris disk that the impact created around the tilted Uranus, inheriting the post-impact geometry as their orbital plane. But it creates a timing problem. For the moons to have formed from impact debris, the impact must have occurred early enough in solar system history that there was sufficient material available to form 27 moons of the sizes we observe. The largest Uranian moons, Titania, Oberon, Umbriel, Ariel, Miranda, range from a few hundred to nearly 800 kilometers in diameter. Forming them from impact ejecta requires a significant amount of material ejected into orbit. The current simulations suggest that a single impact of the scale needed to tilt Uranus does not eject enough material into stable orbit to form moons the size of Titania and Oberon, which has led some researchers to propose that the moons formed first, that Uranus had a pre-existing system of large moons before the impact, and that the impact disrupted those moons, redistributed their material, and the current moon system represents a rebuilt version of the pre-impact one. A moon system destroyed and rebuilt by the same event that tipped the planet. The impact did not just change the planet, it remade the entire system. Voyager 2 is the only spacecraft to have visited Uranus. In January 1986, it flew past at a closest approach of approximately 81,000 kilometers, spending a total of about 6 hours in the Uranian system before continuing to Neptune and eventually into interstellar space. 6 hours at a flyby velocity that gave no opportunity to slow down and enter orbit. Everything we know about Uranus from direct observation, the magnetic field geometry, the atmospheric composition, the ring structure, the detailed properties of the moons, comes from those 6 hours in 1986 and from Earth-based and orbital telescope observations. We have not been back. The Voyager 2 flyby occurred by coincidence at a time when Uranus was near solstice, the point in its 84-year orbit when one pole points almost directly at the Sun. The spacecraft flew through a system that was presenting its south pole to the solar wind, producing a magnetospheric configuration unlike any it would have at any other time in the orbit. Many of the measurements Voyager made were taken in this specific, unusual configuration. How Uranus's magnetosphere behaves during other parts of its orbit, when the equator faces the Sun, when the North Pole points towards the Sun, we do not know from direct measurement. The Planetary Science Decadal Survey, the document that guides NASA's priorities for planetary science missions over a decade, identified a Uranus orbiter and probe as the highest priority large mission for the 2023 to 2032 period. A flagship mission to Uranus, a spacecraft that would orbit the planet for multiple years, measuring its magnetic field, its interior, its atmospheric composition, its ring dynamics, its moons in detail, is the top priority for the next generation of planetary science.
If funded and launched in the late 2020s or early 2030s, it would arrive at Uranus in the early 2040s, more than half a century after Voyager 2. The most tilted planet in the solar system, the planet with the most unexplained properties, the planet whose history contains a mystery written in its very orientation, has not been visited by a dedicated spacecraft in over 50 years. Everything we think we know about what hit it is inferred from the current state of a system we have barely seen. There is a broader context to the Uranus impact that stretches beyond our solar system. In the past decade, the study of exoplanet systems has revealed that large axial tilts are not rare. Several exoplanets have been found with tilts suggesting giant impact histories. Some exoplanet systems show evidence of violent early evolution, scattered orbits, hot Jupiters in unusual configurations, debris disks that imply massive collisions. The early solar system was violent. The early solar systems of other stars were also violent. Giant impacts were not an anomaly.
They were a standard feature of how planetary systems finished assembling, the final clearing of the debris left over from formation, a period of large collisions that settled the planets into their current configurations. Uranus's tilt is not a cosmic accident in the sense of being extraordinarily improbable. It is what a giant impact leaves behind. And giant impacts happened to many planets in many systems during a phase of solar system formation that every system goes through. What is unusual about Uranus is not that it was hit, it is that the evidence of the hit is so visible, so extreme, so clearly written in the 98-degree tilt that no amount of subsequent evolution has erased. Most planets that were hit in the early solar system show subtler evidence, density anomalies, asymmetric cratering, compositional heterogeneities that require explanation. Uranus shows its impact the only way a planet can show something of this magnitude. It is still falling from the blow, 4.5 billion years later, still rolling sideways through space. Look at Uranus through a telescope on a clear night. It is visible to the naked eye under good conditions, barely, as a faint greenish-blue dot, indistinguishable from a dim star without optical aid. Through a modest telescope, it resolves into a pale blue-green disk, featureless at most magnifications, serene in a way that gives no indication of its history. That serenity is the result of whatever hit it. The extreme tilt means the atmosphere circulates differently than on any other giant planet. The polar regions receive intense solar input for decades, and then nothing for decades. The equatorial regions receive gentle, shallow-angle illumination year-round. The result, paradoxically, is an atmosphere that is remarkably uniform in temperature from pole to equator, unlike Jupiter and Saturn, which have strong equatorial to polar temperature gradients that drive their banded atmospheric structure. Uranus's atmosphere is calm because it was hit. The violence of the impact produced the stability of the atmosphere. And somewhere inside Uranus, in the icy interior that we have never directly sampled, in the layers of high-pressure water and ammonia and methane that make up most of the planet's bulk, there may be material from whatever hit it, mixed into the interior, chemically indistinguishable from the original Uranian material after 4.5 billion years of pressure and heat. The impactor is inside the planet. The planet absorbed it and kept falling sideways. We have never found the thing that hit Uranus. It is not surprising. The impact happened at the beginning of the solar system. Any remnant of the impactor that was not absorbed into Uranus was scattered, sent onto new trajectories by the energy of the collision, mixed into the general population of debris in the outer solar system, eventually either absorbed by another planet, ejected from the solar system entirely, or degraded over billions of years into material unrecognizable as the remnant of the object that changed a planet's axis. The impactor is gone. It left its mark, a 98-degree tilt, an anomalously cold interior, an off-center magnetic field, a moon system orbiting in the plane of the equator, and then ceased to exist as a coherent object. The evidence is written in the planet. The cause is unrecoverable. This is the character of deep-time geology and deep-time planetary science. Events leave records. The records are readable, but the events themselves are gone, and what we reconstruct from the records is always an inference, better or worse constrained by how good the record is and how well we understand the physics. The record says Uranus was hit. The record says the impactor was large. The record says the impact was early. Beyond that, the record runs out, and the planet continues its sideways roll through the outer solar system, 98 degrees from where it started, carrying inside it the unanswered question of what was violent enough, fast enough, and large enough to knock a world that size permanently off its axis and leave no trace of itself behind, except the tilt.